Okay, looks like we have 26 participants. Lisa, shall we get started?
Yes, that sounds good. Thank you for joining us this morning for day one of a two-day HPRC short course entitled Introduction to LAMMPS. It is my pleasure to introduce the instructor for today's short course, Professor Michael Demkowitz. Dr. Demkowitz is an associate professor in the Department of Material Science and Engineering here at Texas A&M University and the director of the Center for Research Excellence on Dynamical Deformed Solids. If you have any questions during the presentation today, please post them in chat or raise your hand. Again, let me welcome everyone, and with that, I will pass it over to Dr. Demkowitz.
Thank you. So I'm glad that we have a good turnout, 26 of us, and my understanding, Lisa, correct me if I'm wrong, is that this is going to get recorded and eventually posted on the HPRC website?
Yes, that is correct, in our YouTube channel.
Okay, very good. So as of my understanding is that as of yesterday, all of you should have already received your net IDs. And my apologies that it took longer than expected. I don't know if I mentioned this during the opening of the OREU, but normally if we have a OREU student joining us for the summer, they simply get hired as an employee. But to get hired, you have to have at least one in-person meeting. And so obviously we couldn't do that. So we had to come up with this other way, and there were some hiccups and snags, and and inevitably this is the first time we've done it this way. So thank you for your patience. I'm glad that it took us only a week to get things sorted out. So thank you again, and hopefully you're all set. So what I'm going to do here real quick is I'm just going to share my screen, because everything that we're going to be doing here is going to be done via the HPRC portals, which you should all be able to access. So first thing that you should do is go to your VPN clients, so the Cisco AnyConnect client, at least on Mac. I don't know what it would be on Windows, but hopefully you guys have all activated this already, right? Has anybody not activated this? Say in chat if you've not activated your VPN client. I think that if you applied for a basic account, then you must have activated your VPN client, because I don't think it lets you apply if you don't have this. So I'm just going to assume that you all have this. If you don't have it, you're going to get stuck at this point and you're not going to be able to go any further. So hopefully you all have it. So I'm going to just connect, put in my password. I'm going to get a little ping on my computer, on my iPhone here. So I'm going to authentication. Here I am. And now I just go to my favorite web browser, and I open up portal.ada.hprc.tamu.edu. Okay, you guys see that? portal-ada.hprc.tamu.edu. Press OK, and you should get here. Okay, I'm going to pause for just 1 second to see if anybody has any troubles with this. I see that Lisa posted the address to the chat. So if you couldn't see what I wrote there, just go to the chat box and pull out the portal address from there. Okay, I'm going to assume that everybody's in. What we're going to do now is we're going to launch an interactive app. Right, so we go up here to the menu, Interactive Apps, and we're going to do VNC. Okay, this is what you should get when you go to VNC. And there's a couple of fields here that you're going to have to put in. We're going to put in number of hours 4. This whole session is going to last 3 hours, so 4 is kind of on the safe side, let's say. And we'll put in 1 core because we're not going to be using any more than 1 processor for today. Memory per core, the default is 2 gigabytes. You can leave it at that. Node type any. Account and email you can leave blank. And then you just press launch. Okay. So when I press launch, it should take me to a screen like this. And now I just sit here and wait for just a moment while the session gets set up. Once it gets set up, I should see a button showing up here, which is going to allow me to launch. There it is. Okay, you see this after just a few seconds, you should see this button showing up. Press that button. That should pop open a new screen for you. So here's my new screen. And this is a virtual desktop. at the HPRC computers. Now, anybody who has worked with Linux before and a command prompt before knows that you can also log in just via a regular X-terminal window. Mac comes automatically. If you have a Mac computer, it automatically has an application that does that. For Windows, I think you might have to download one, but it's fairly easy. You can log in directly through an X-terminal to HPRC. And if you have X Windows installed, then your computer desktop will act as a terminal for HPRC. So that's another way to do it. And if you are going to be doing a lot of work at HPRC running these kinds of command prompt applications, then I definitely do recommend that you get that installed. But for today, this is going to be more than enough. And and if you don't mind using this kind of interface for your work, then you can also just use this on a day-to-day basis for everything. I'm just going to go back for a second to my interactive sessions here. So I'm just going to go back here. In addition to the interactive apps that you can work with through HPRC here under this menu, you also have this other menu here called Files. And this Files menu allows you to upload and download files from your account. Okay, so each one of you has an account at HPRC. And you have the ability to put files in there. Now, when you click on this menu, you're going to have a home directory and a scratch directory. In everything that we're going to be doing today, please do not use your home directory because that has very limited memory. Instead, we're going to use the scratch directory, right? So each one of you should have a scratch directory, and the name of that directory is /scratch user and then your net ID, right? So net ID is whatever comes before the @ in your @TAMU account. So my net ID is my last name. I'm just going to press this here, which is going to open up for me a window, which allows me to upload and download files, right? And this basically just shows you what I already have in my scratch directory, okay? And if I wanted to download something, for example, let's say I want to take one of these files. I want to download a file. Oops, no file selected. So let me select a file. Let's say this one, download. Do you want to download? Allow, okay? And it goes down into my downloads folder. There it is. Okay, so now I moved it off of HPRC onto my own computer. Of course, I don't need it, so I'm going to throw it away. I can also upload. So here's my upload. If I want to upload, I press upload, and it prompts me to choose a file. If I press choose file, I just get this regular sort of thing where I can go through, choose a file, and then when it uploads, it uploads. So I'm not going to do that right now. Basically just wanted to show this to you that you can at any time upload and download files to and from your computer onto the HPRC account that you have there. Okay, so let's go back now to this session here, and let's go into this terminal here. This is a command line terminal. Some of you have had experience with this. Those of you who have not had experience with this may have participated in some of the HPRC tutorials which talked about this. Those of you who have not had experience with this and were not able to participate in the tutorials, you can, I think, view those tutorials online. I believe Lisa has links that can take you to those tutorials. They're also on the HPRC website, which is linked from the OREU website. So you should be able to do that. Let's real quick, if you type PWD in here and press return, that's going to show you where you are now in the directory structure of the HPRC computer. Okay, so right now I'm in my home directory. As I said, we're not going to be uploading any files to the home directory. So none of the files that I showed you previously, these files over here, none of them are going to show up here. If I want to see what's in my home directory, I press LS. Here's what I have in my home directory. None of these files that you saw over here show up in my home directory. What I need to do to see these files, I have to move to my scratch directory. So let me do that. CD means change directory. I type scratch, okay, scratch. You remember the name of that directory was scratch slash user slash your net ID, okay? So scratch slash user slash my net ID. There I go. And when I press return, I've changed my location. If I do PWD again, I'll see where I am. Now I'm in the scratch directory. And if I do ls, which shows me what's inside the directory, you see that all those files that I had back here, these guys, are now showing up because now I'm in the Scratch directory. Okay, has everybody been able to move to their Scratch directory at this point? Anybody not been able to move to their Scratch directory? All right. I'm going to go ahead and actually delete a lot of these files. And while I'm doing that, I'm going to teach you a little trick. So you see that some of these files have rather long names, and you'd rather not have to type them out. If you type in the first few letters and you press tab, the command line is going to auto-complete that for you. So if I do rm cu subscript m and press tab, then it auto-completes to the only file that begins with cu_m. Okay? So if I want to remove that, I press rm, now it's gone. All right, so I'm just going to remove the rest of these as well. I don't need them. I was using them before just for some trial runs, but now I don't need them. So I'm going to get rid of them. And now we do have some files that I've prepared for you to work with in this tutorial. So we're going to get those files, and I'm going to just open up my Slack channel here. And Lisa was telling me just a moment ago how to do that. So cd $scratch. Is that something that just takes me to my Scratch directory? Yes. So you guys are already here. And now we unzip this. Okay, so hopefully you guys can all see this. Unzip this stuff right there. By the way, if you want to cut and paste things from your computer to this desktop, it's a little bit clunky. I'll show you how to do it. I'm just going to do Control-C here because that just copies in my screen here on the Mac. If I move back here, I can't just do Control-V. It's not going to show up. If I do Control-V, I get some weird umlaut. I have to put it into the clipboard, and the clipboard is here. So I'm just going to put that into the clipboard. Okay. And now if I right-click, which on my Mac is if I press down with 2 fingers, that's a right-click. It should show up, but it's not. Okay. All right, so never mind. So I guess that's not going to work. I'm just going to have to type this. Unzip /scratch/training/intro_lamps.zip. And I'm going to try to use my autocomplete when I do that. Unzip Scratch. There we go. What was the next one? Training. Okay. And then intro lamps zip. Okay. So there we go. I'm going to press that, and there it goes. All right, what do I got here? Intro lamps. I'm going to change directory to intro lamps, and there I am. All right. Let's go to 1, visualizations. And you have here the materials that we're going to need for today's class. You see that one of the things that you have here is the tutorial. Okay, tutorial subscript 1-visualizations. This is a PDF file. I believe you should be able to open it with XPDF. Let's see if it works. Nope. PDF? Nope. Lisa, what do we use for PDF on HPRC?
I would suggest that you go to the other tab with the files and open it
download
there.
it? Okay.
Or open it directly in there.
Okay, I'm getting a bunch of questions here. Let's see. Lars, cannot find our open now. Okay, never mind. How to magnify terminal. Lisa, presumably you're monitoring the chat?
Yes, yes.
Okay, great.
So I
All right.
believe that you can increase your text with the Command plus or the Control Shift plus. Can you try that, please?
Let's do Command plus. Nope.
No. The Control
Shift plus. Nope.
Nope. Okay. Give me just a minute and I'll figure that one out. I've forgotten. Probably in there also.
I'm going to leave that to you guys. So you can go over to your file explorer. I'm just going, what should I do here? Should I see if renewing this. Okay, great, that works. So I just reloaded. Intro to LAMMPS. If you go to visualizations, here's your tutorial. You can download this file if you want. Okay, you can download it onto your computer and just view it on your native PDF viewer. I have the file already open here on my computer, so I'm just going to open it up for you. In this file, the first thing that happens is it moves through some of the stuff that we already went through. So I tell you about the portal, VPNing, what kind of settings you should use here, how to move to your Scratch directory. And the next thing that we're going to do is we're going to set up the environment to use Atomai on your account. Okay, so we're going to have to go back to the command line and issue the command ml atomai/a3. All right, so let's do that. Let me minimize this. Okay, ml atomai/a3. All of you should be able to do this now. Takes a second, and after just a moment, you should get a success. There it is. All right, it worked. Great. So what is Atomai? Atomai is a little program that lets you view atomic models, right? So LAMMPS is an atomistic modeling package. Atomai is a piece of software that lets you view those files, those atomistic modeling files. It's a code that was written by Professor Ju Lee at MIT. He maintains it on his website here. If you press it, it'll open up to that website. There it is. It has all kinds of interesting stuff there, including manuals, and tells you a little bit about the features and the file formats. There's a gallery here of different things. So we're going to use this gallery real quick. I'm going to just press this dna.pdb file. Sorry, maybe not the picture, but rather this file here. And it asked me whether I want to download it, and I'm going to download it. Okay, so I'm going to download this to my downloads folder. There it goes. And now I'm going to go back to my file explorer, and I'm going to upload it to my visualizations folder. So I'm going to upload, choose file. It's in my downloads, dna.pdb, choose, and there it goes. Now when I go back and I do ls, I should see it. There it is, dna.pdb. Everybody see it? I'll give you just a moment to do this yourself.
Oh, Michael, if you go to another tab and you use the command plus, it will let you zoom your web browser. So when you go back, the text will be bigger.
Okay, you mean if I
you can use the menus. Just go to view and zoom
view.
in the main menu.
Is this the view? No.
No. In the main menu for Safari, sorry.
Aha, here?
And if you do the zoom in, you can't use the keystrokes.
Okay, all right.
But that will let you zoom in and out.
Cool, great. Hopefully this will be, let me zoom in a little bit. You guys will probably see this a little better now. Good. Let's see. So the copying business is a little tricky, as I mentioned just a moment ago, but I think if you use the autocomplete, it lets you get those long things written out relatively fast. Okay, I'm not seeing anybody saying that they don't have this dna.pdb thing yet, so I'm just going to go on to the next thing. Hopefully, you all have this DNA file. What I'm going to do now is I'm going to type A3, and DNA. I can autocomplete it. All right, so there it is, and I'm going to press return. And I get this kind of window opening up. Has everybody been able to get this far? Or has anybody not been able to get this far? Anybody have trouble with this? No? Okay. This is now a window that you can move around. I'm going to move it around a little bit. I'm going to increase the size just so I can see it a little better. All right, there it goes. It should automatically resize. And you see a bunch of atoms. What command did I just use? You mean to run this code? I said A3. So let me back up a little bit. Actually, let me just start over. I'm going to close this. All right, guys, keep up. And if you get stuck on something, please please be sure to ask. Okay. I'm going to relaunch this VNC window here. Failed to connect to server. I don't know what's going on here. Do I need to delete and restart this, Lisa, or can I just launch?
Try relaunching it. Okay, so if you close the terminal, you have to relaunch one.
Okay.
So go ahead and close that tab and
delete
that one and make a new one.
All right.
So you have to keep that original terminal open.
Gotcha. We'll run through this one more time just so everybody's on the same page. Okay. So this is an interactive session. The idea is that you follow along. So please do try to follow along. And if anything doesn't make sense or if you get stuck on something, please do put something into the chat, and Lisa will let me know, and I'll slow down, and she might also just answer your question in the chat as well. Okay, so here I am on the portal-ada.hprc.tnu.edu site. Was everybody able to reach that? Anybody not able to reach this site? Nobody is saying that they can't reach this site, so I'm assuming that you're all on this site, okay? Let's go to VNC, all right? Go to VNC. I'm gonna set up my session again, launch. Okay, just gonna wait a second for it to come up. There it is. All right, and here I am in my window again. All right, so as I mentioned, we want to go to Scratch. So I'm just told that you can do CD $Scratch. That'll take you automatically to your own Scratch directory. Yeah, there I am. Okay. Now, let me just restart this whole process of getting the files. So I'm going to get rid of this directory here, and I'm going to once again unzip Scratch training intro lamps.zip. Okay. And before I press this button, I'm just going to ask, is everybody in their Scratch directory at this point?
Many people are having trouble seeing the size of the text. So if you could zoom in.
Zoom in some more. Okay. All right. Zoom in. Oops. Okay, I think that's the maximum. Awesome. Okay, great. Awesome. I'm really glad when you guys tell me when stuff is not working, right? Because if stuff's not working, then I'm talking to a wall and nobody benefits. So please, 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 if something's not working, if you're stuck on something, please do say something. We want to make sure that everybody follows along and is able to participate. So has everybody been able to change directory to their Scratch directory? If you press PWD, if you type PWD, you should see Scratch user and then your net ID. Is anybody not at this stage yet? Has anybody had difficulty reaching this stage? Okay, nobody's saying anything, so I'm going to go to the next point, unzip. Okay, and now I have two options. I can either type out, by manually this thing, /scratch/training/intro_lamps, etc. But I can alternatively just start typing it and press tab, and you see that it auto-completes because there's nothing in the directory structure that begins with SC that is not Scratch. Okay, so the tab auto-completes to whatever is the unique thing. And if it happens not to be unique, then it will only auto-complete to the point that it can. Try it out. I mean, you'll learn how to use this really fast. It's one of the things that you sort of pick up very quickly when you start doing command line. So so I just typed TR and press tab, right? And that auto-completed the training thing. Intro, when I press tab, doesn't auto-complete all the way because presumably there are other things there that begin with intro that are not lamps. If I press tab a few times, it should show me what they are. There it is. We have intro lamps, the unzipped version of intro lamps.zip, and we have intro to NGS and then intro to Unix, right? Other intro courses that HPRC runs. So intro, we have intro underscore. I haven't finished yet, so we have to do L and then press again. That auto completes to lamps, but not lamps.zip yet. Okay, and then dot and then zip. So this is what you should see before you press return. Unzip space slash scratch slash training slash intro underscore lamps dot zip. Okay. And then once you're at this point, once everything is done, then I press return and you should get a bunch of this text showing up. And you're back to your command line, okay? This is not quite the right size, so let me see if I can increase the size here so you can see the bottom of my yeah, there we go, okay, good. Great, all right. Now, everybody should have this thing here that says intro to lamps. When you do ls, that shows you what's in your directory. This blue thing here, intro to lamps, is a directory, or intro underscore lamps. So I'm going to do cd intro to lamps, okay, ls, this shows me what's inside. And now I'm going to do one more time, cd -- autocomplete visualizations, and then again ls, and I'm in my folder that deals with visualizations, which is the topic for today's tutorial. Okay, everybody with me so far? Okay, I assume that you guys are all with me. Now, as I said, if this tutorial right here, this file, this PDF file, if you want to view it, I think the easiest way to do it is just you go back to your VNC interactive session, and you go to the, you remember how I was telling you that there's this files thing up here? You can choose files and go back over, and it should open up a window like this. This is going to allow you to download this file. So if I press this tutorial file, and let me actually reload this because I think this is the old one. So let me go back here. If you go back here and go to files and choose your Scratch directory, it should open up a new window. Okay, so there's my new window. And you see that it's got my intro to lamps directory that I just installed. I'm going to double click that. It's going to take me inside. I have my visualizations folder. I'm going to double click that. It's going to take me inside that. Here's the tutorial file. I'm just going to press on that and press download. And then it downloads to your download folder and opens up. Okay? Can everybody get access to this file? Okay, great. It seems like everybody is getting access to this file. If you're not getting access to the file, by all means, please say so. You know, it's entirely possible that there was a hitch along the way. We do want you to, you know, be caught up with us. So please do let us know and we'll help you. This file, as I mentioned, is just a file that sort of outlines all the stuff that I'm talking about. That I'm talking about here. In this tutorial, beginning with all the stuff that I told you about signing on to VNC. So whenever you want to run your own simulations, you can use the same portal to run your simulations, or you can, you know, use a direct login through an X terminal, whichever way you prefer. There's also a link here to a YouTube video that shows you how the portal works. So if you have any trouble, you can always do that. Look at that. So it talks about some of the stuff that we did. And then one of the things that I mentioned previously that we're going to have to do next is since we're going to be doing, you know, in this tutorial here, we're going to be talking about visualizing atomic structures. We're going to be using this utility or this little code called Atomi. And for Atomi to be able to run, on your virtual session here, you have to go back to that virtual session, which I'm going to do here, and type ml atomi/A3. Okay, so I'm just copying in the thing that's in the tutorial document. Type that in, press return. It takes just a few seconds, and eventually it gives you a success message, and then you're ready to run Atomi. Okay, this is basically something that just tells the computer that you're going to run this software and that the software should be made available in your session that you have open right now. Okay, so that's easy. Now, I'm going to transition to talking a little bit about Atomi itself. And as I mentioned previously, I have this website that's linked here in the tutorial document. This is a live link, so if you press on it, it should open up in your web browser. This is just that link that I pressed in the tutorial document. It opens up in the web browser. It's got a bunch of stuff up here. It just has a lot of information about this particular piece of software, which I use for visualizing atomic structures. Okay, if I press gallery, it shows me all the different things that I can look at using this piece of software. These are just examples, of course. People have made all kinds of different things, all kinds of different models. There's a DNA model, there's a nanotube model, there's a polycrystal model, there's a screw dislocation dipole, there's some crystalline and amorphous structures. This is an indentation with a dislocation, I think. So there's a lot of different things that you can visualize. And if I press on one of these images here, it gives me a zoomed in version of this image. This is the DNA file that we're going to be looking at. And if I press on the link underneath the image, that's going to download the file that contains this structure. Okay, I'll show you in a minute exactly what the structure looks like and then what's in the file. But for starters, just press this link and it should download for you the structure to your downloads folder. So here's my download folder. It now contains the visualization tutorial that I just told you about, and it's got this dna.pdb file. Okay. Hopefully you're all caught up with me to that. So I'm just going to go back now to my file transfer session, which is this. Okay, this is where I do my file transfers. I'm going to go up to this button here that says upload. I'm going to choose upload. It pops up a window that prompts me to choose a file. So I'm going to press choose files. I'm in my downloads folder, so I'm on a Mac, so I select downloads. Once I'm in there, I have the choice of these two files that I've downloaded to my computer, and I'm going to choose dna.pdb, okay, because that's the file that I want to move from my computer to the HPRC computer. I'm going to choose that. And as soon as I choose that, it shows up here. Okay, so that means it's uploaded. It went. It's a small file, so it doesn't take long to upload. Now I'm going to go back to my terminal, and I'm in my visualizations directory, so I'm just going to do ls. And when I do ls, you see that this dna.pdb file now shows up in my directory. Okay, so was everybody able to do this? Was everybody able to get their dna.pdb file uploaded to their HPRC session? Okay, I'm looking at my chat screen here. Nobody's saying that they can't do it. You should upload it. You can upload it anywhere, but I would upload it to the same place where you got this tutorial, right? The tutorial subscript 1-visualizations, upload it there, right? Again, you can upload it anywhere you want, but I suggest uploading it there because if you just start putting it anywhere, you're going to forget what it is, where it is. You're going to put it into a folder that corresponds to one of the other tutorials. Just in the interest of keeping things organized, my recommendation is just put it into your 1-visualizations folder. Okay, and I'm just going to go back here. The way that you do that is you navigate to that folder in this file here, in this session here. Okay, I'm just going to click this a couple of times. Right here is my Scratch directory. Okay, this is the Scratch directory. When you did the unzip command, it gave you this directory, intro subscript lamps. I'm going to double click on that. That takes me inside my intro subscript lamps directory. I have 3 different directories in there. One of them is called 1-visualizations. I'm going to double click on that. Okay, that takes me in here. This is where I uploaded. I was at this point when I wanted to upload this thing. Okay, so when you're in there, you can do upload. By the way, if you want to move down in the directory structure, you just double click this double dot. Okay, and then I can move up and down like that. If you inadvertently uploaded this to some other place, just let us know. You can move files around in the command prompt, so we can show you how to move files around. That's not a problem. Okay, but it's easiest if you just upload it directly to where you want it to be. All right, so I'm going to go back here to my visualizations directory. I've got my dna.pdb file. Actually, before I visualize it, before I open it up, I'm just going to do one simple thing. I'm going to say more DNA, right? This more command is a nice little command which basically just shows you the first few lines in the file. Okay, so and you can see on the bottom left here, down here it says 3%. So it's actually just showing you 3% of the file right now. It's just showing you the first couple of rows in that file. If I press the space bar, it'll keep showing me the further rows, right? So as I keep going down, it's showing me more and more and more of those rows. And you can see that all the rows are atoms, right? So each row starts with atom. It has a number, which is just the number of the atom. It has then a label, which tells you what kind of atom it is. C means carbon, H means hydrogen, O means oxygen. It's got this other stuff here, right? This is a DNA molecule, so it's got ATP. Each atom is labeled according to whether it's part of an ATP group. I'm not sure I remember what this column was for. But the other columns that you see here, these columns are showing you just coordinates in space, right? So they're showing you basically where is this atom located. And whenever you talk about an atomic model, this is really all you mean, right? An atomic model is just showing you locations of atoms in space, okay? Of course, all of you know that atoms consist of nuclei and electrons, but in this session and in all the sessions that I'm going to do on LAMMPS, we're going to completely ignore the electrons. We're only going to think about the nuclei. When we talk about atom positions, we're talking about the atom nucleus positions, right? And you might say, well, how can you ignore the electrons and and only think of the nuclei? Well, if you're interested in figuring out how the atoms move around, right? So basically, what is their dynamics? You know that almost all the mass of the atom is in the nucleus. So if you're interested in where the atom is and what's its inertia and how does it move around, ignoring the electrons is not a big deal, okay? Because they don't really affect the mass. And if you're interested in the inertia, and that's going to really, determine how the atom responds to forces, right? Then the nucleus is all you need, all right? But some of you might remember from your solid state physics classes, you might say, but wait a minute, don't chemical bonds come from electrons? Don't the valence electrons determine the chemical bonds between atoms? And the answer is yes, they do. Those chemical bonds, of course, come from the electrons. And of course, the forces on the atoms come from the chemical bonds. So if you want to know the forces on the atoms, really, you should be solving Schrodinger's equations and figuring out the bonds, and from the bonds, figuring out the forces, all right? And of course, some people do that. Those methods that use electrons to find forces on atoms are called first principles methods. First principles methods are not what I'm going to be covering in this tutorial. I'm going to be covering what are called classical potential methods. LAMMPS is a classical potential code, and don't worry, I'm getting a little bit ahead of myself here, but I just wanted to give you a little bit of context. It's a code where instead of solving for the forces using Schrodinger's equations, we say, actually, we already understand a little bit about how bonding works. We can probably just write down equations for what the forces on the atoms should be, okay? And those forces are what are called, are derived from what are called interatomic potentials. The advantage is that if you don't have to solve Schrodinger's equation, the code runs much faster, it's much more efficient, and you can run much bigger models, okay? So that's just to give you a little bit of context. That's why when you open one of these structure files, you see coordinates of atoms, but only of the nuclei and nothing for the electrons. Okay, so this is just to give you a little bit of context. All right. But this is also showing you what an atomic model is. I'm not opening this file, by the way. I didn't open it. All I did is I said more, and then DNA, and press return. Okay. What that does is it doesn't open the file. I don't get to edit the file at this point. All it does is it shows me on my terminal window the first few lines of the file. So it's just something that views. All right. I can't edit anything. It only shows me, in this case, whatever fits on the terminal window, which is not the entire file. It's actually only 3% of the file, as you can see here. And if I want to sort of scroll through and see the other bits of the file, I can press the space bar, and it'll basically just show me more and more and more of the file. Okay, and whenever I'm done, and whenever I'm bored looking at all of these rows of atoms, I can just press Q and that exits. Okay. So there I am. There's my file. And I know now that it just contains a bunch of rows which specify the individual atoms, their positions, and their types, basically. That's all that an atomic structure is. Of course, looking at a file that's full of coordinates doesn't really let you appreciate what structure you're looking at. It makes much more sense to take this structure and render it, right? Have a graphical rendering that shows me what that looks like. And that's what Atomi does. Atomi is going to let me look at what this file actually shows. And so to run Atomi, I'm going to type A3, okay, space, and then the name of this file, which is dna.pdb. Okay, and once again, I used autocomplete. So A3-dna.pdb. That's what you should type. And whenever you're ready, press return, and this is what you get. Okay, because I zoomed in a lot, this looks quite granular. So I'm just going to zoom out for just a second. I'll zoom back in when I have to actually do some more typing here. But for now, I'm just going to zoom out a little bit so this doesn't look quite so granular. Okay, zoom out. All right. And here's this is just a window. I can carry this window around just by clicking and dragging it like I would on a regular desktop. And I'm going to resize it. I'm going to make it a little bigger, right? So I'm going to just, resize this window to make it a little bit bigger. It should adjust so that you can see everything. When you look at this, you say, wait a minute, this looks nothing like what I saw in the gallery. If I go back to the tab with the gallery, this is what I saw in the gallery, right? So you can say this looks nothing like the gallery. Why does it not look like the gallery? Okay, and the reason why it doesn't look like the gallery is perspective. Okay, if I want this to look more like the gallery, what I'm going to do is I'm going to hover my cursor over this window, and I'm going to press and drag, and that's going to rotate the structure in the file. Okay, so I'm going to press, and now I'm just going to drag the cursor, and you can see this structure starts to rotate. And when I rotate it around, I can see it starts to begin a lot more like that DNA structure that you saw in the gallery. Okay. Now you'll notice, those of you who are artists recognize that this is showing you the whole structure with a sense of perspective, right? Meaning that the atoms that are closer to you look bigger, the atoms that are further from you look smaller. The face of this model, which is closer to you, looks bigger. The face that's further away looks smaller. Maybe you like it that way. Maybe you don't like it that way. If you don't like it that way, you can just press Tab, and that's going to put you into Orthonormal View. Orthonormal View basically shows all atoms at the same size regardless how far they are. So basically that takes away the perspective. And I believe this is perspective view. The Atomi gallery showed you perspective view. If you like perspective view, you can use perspective view. And if you like orthonormal view, you can use that. Tab will basically just toggle between those two options, right? So if I press Tab, it's going to toggle between those two things. Okay, everybody with me so far? Anybody not able to open this file? Great. So I'm guessing that everybody's with me. When you go back to this gallery file, you can go through and download any one of these other structure files that you see here. Except I guess this one doesn't have anything linked to it, but all the other ones have a link. So you can download a link to those files, visualize the files, look at them, see what they look like, play around with them. So I encourage you all to do that on your own time. It's sometimes fun to do that. Okay, a couple of other things that I wanted to point out while I'm here. You see that this DNA model sits in a box. This is called a simulation cell, right? So the simulation cell basically delimits the size of your model. A model of an atomic structure is a finite thing. It's not infinite. It doesn't sort of extend to infinity in all directions. It's got boundaries. It's got bounds. Okay, and these black lines here are showing you the bounds of the simulation cell. Okay, so basically the size of the model. If you've done any sort of other simulations in your life, you probably realize that whenever you run a simulation, for example, if you're solving a boundary value problem, like you want to solve a partial differential equation, like the diffusion equation, or one of the elasticity equations of mechanics, or if you want to solve the wave equation, any one of those things you want to solve, you have to specify boundary conditions. You have to tell your solver what happens at the boundaries of your model. That's also true in atomistic models. In atomic models, you also have to say what happens at the boundaries, and there are lots of different things that you can choose to happen at the boundaries. But the most common choice, the thing that most models use, is what are known as periodic boundary conditions. Periodic boundary conditions are boundary conditions where I like to call them the Pac-Man boundary conditions. So those of you who have played the game Pac-Man before know that Pac-Man exits through one side of the screen, and as soon as Pac-Man exits from one side of the screen, he reappears on the other side, right? So he leaves from one side and he comes in from the other side. So basically, that's periodic boundary conditions. Periodic boundary conditions means anything that leaves, through a simulation cell going to the right, re-enters automatically from the left. Okay, and how can I see that in the case of this DNA model, where, well, Atomi allows you to actually move the structure around inside the model. And when you move it around, you're going to see that you can actually make the atoms exit from one side and enter from the other side. So to do that, you do the same sort of click and drag thing, but before you do that, you press Shift. So Shift, click, and drag. And you see that's going to translate the model, right? And if I translate it up and down, right, then you can see that it's going to leave through the vertical surface and come back. So if I have atoms leaving through the upper part, you can see that they're reappearing on the bottom part. And if I shift it to the left, you can see atoms leaving on the left, appearing on the right, right? And if I keep dragging, if I drag enough, eventually the whole thing's gonna, and of course now this is also shifting around through the other direction, which I didn't have really good control over. So let me shift it again. If I keep shifting it, eventually I'm gonna regain the same model as I had before, but having moved the whole thing through one of the periodic boundaries. So I hope this gives you a sense of the boundary conditions that we're applying in these models. They're periodic boundary conditions. Does anybody have questions about periodic boundary conditions? Let me see where I am here. Periodic boundary conditions. Okay, I'm assuming that everybody has made it through this far and has been able to do all this sort of rotation and shifting and everything, and as well as the periodic boundary conditions. So I'm almost done introducing Atomi to you. Just a couple of things that I wanted to say. One of the reasons that I like Atomi is because it's really, really easy to use. For example, if you were running a simulation and you were using Atomi to visualize the output of your simulation, and you wanted to make a picture, right? You wanted to record an image that you could actually look at afterwards, and maybe use it in one of your presentations or a paper or report. Atomi allows you to very easily do that. When you're in the Atomi screen, all you have to do is press the letter J, right? And you see you have something that appears here immediately on your command prompt. It says save on screen dna.jpg. It allows you to save a JPEG. You're just going to press return, and it's saved basically a JPEG of whatever I have on the screen. If I don't like what I have now, I can change it. I can change it to perspective view. I can rotate it around, press J again. It's going to ask me again. I can either press return again, in which case it'll overwrite whatever I had before, or I can type in a new name. For example, I could write dna2.jpg and press return, and then it won't overwrite. It'll just write a new file with the new name. Okay, so Atomi allows you to do that very easily. So I'm going to quit Atomi in just a moment, but first of all, I just wanted to mention, whenever you run Atomi, it actually occupies your command prompt, right? So your command prompt right here is now occupied. You can't, navigate in your directory or open other things while Atomi is running over here. So the easiest way to get around that is to just open another terminal window. And one way that you can do that is just right-click. If you have a Mac, to right-click, all you have to do is press down with two fingers, and that does a right-click. And if I scroll down to here, you see that I've got an Xterm option. If I press Xterm, it opens up another window for me. Okay, so if I'm here, if I've opened Atomi and I can't really use my terminal window over here, but I'd like to issue some new commands, I can always open a new Xterminal window, and this puts me in my home directory. So I can do cd $scratch, and that'll take me to my Scratch directory. Yeah, there I am. Okay. So I'm just going to shut that down. I'm also going to shut down Atomi, right? So I'm going to press this to shut it down. As soon as I shut it down, you can see that I regain control over my command prompt, right? So here I am in my command prompt again, right? I'm going to increase the size here. Okay. Zoom in. Okay. All right, so I've zoomed in. When I do ls, you see that I now have, in addition to everything that I had before, I now have dna.jpg and dna2.jpg. Those are the two files that I saved. If I go back to my file transfer thing and reload, I'm going to reload the page. These now show up, right? So I could, for example, select this one and download it. And then it opens up here on my desktop. I have a saved JPG image of my DNA structure that I just saved. And if I don't like the perspective view, I can download the first one that I saved, which is, I believe, the orthonormal view. Yeah, there it is. Right, so I now have access to all of that on my computer. All right. Atomi is a program that you can use on your desktop or your laptop as well. And so if you go back, there's my daughter. If you go back to this link, okay, this Atomi website, you will somewhere over here see download. Okay, so there's download. There are a bunch of different possibilities for downloading, right? So you can download a Mac OS version. You can download a Linux version. There's a Windows version that works with an Xterminal that you can get for Windows. So if you want, you can try adding Atomi to your desktop or laptop. That might make it easier than using it via this remote virtual terminal, whatever you prefer, right? So it's got some information here that will help you. Another option that you could pursue, right? So there are many different programs for doing visualizations, and Atomi is just one of them. Another one that is very commonly used is called Ovito. Okay, so I'm just going to do Ovito for you here. And don't worry, I'm not going to ignore my child. I'm just going to shut off the monitor for just a second. So this is, there's also another program called Ovito. I'm not going to cover Ovito. Oops. Okay, I'm not going to cover Ovito, but actually 3 of the participants on this call right now are OREU students in my group, and they have agreed to set up a session to introduce any of you who are interested in using Ovito. Just contact them. I'm going to type their names here. Matt Cleveland. Hopefully I typed all your names correctly. So Matt Cleveland, Advika Chisetti, and Christopher Wheatley have all agreed to help you get started on Ovito if you prefer to use that that package to do your visualizations, to actually view your atomistic models. Ovito is something that you can download onto your desktop or laptop a little bit more easily than Atomi. So you may prefer to use that if you want to do things on your sort of local computer. And Mac, Advika, and Christopher, if you would just chat your contact information to the group. For example, if you want to chat your email address that you prefer, then people can contact you, and if they're interested in setting up an Ovito session, then you guys can basically just set that up via your own Zoom connection and proceed from there. All right, we are right now at 1 hour, and I have to go take out my child. So I suggest let's take a 10-minute break, and then we'll reconnect in 10 minutes and continue the session there. Okay? So everybody's seen, nobody's protesting. So let's take a 10-minute break, and I'll see you in just 10 minutes, 11:10. All right, thank you very much. All this stuff I think is unchanged. It's looking different because I increased the size of the font. So now I have to sort of get used to this again. All right, and now I'm just gonna wait for that thing to pop up. Let me just do a very quick poll while we're waiting for, there we go. Let me just do a very, very quick informal poll. How many of you have Matlab already installed on your computers? So not, here on HPRC, but how many of you have Matlab actually on your desktop or laptop? So if you've got Matlab installed, let me know. Or maybe the better thing to ask would be, how many of you don't have Matlab? How many of you don't have Matlab installed? Okay, there's a couple who don't. All right, so some do, some don't. Those of you who do, oh, actually a lot don't. All right, so so the next part of this tutorial will involve, I'm going to use Matlab. You don't have to use Matlab for what I'm about to show you, but you can use something else if you prefer. You can use Python, or you can use some other software. Maple used to be popular. I don't know if anybody uses it anymore, but basically, if you have Matlab on your computer like I do, you can just go and click Matlab, and it should open up Matlab. And I believe Matlab is on my computer is probably going to be the easiest thing for me to use. But the good news is those of you who do not have Matlab installed on your computer will be able to run it via your VNC window. So this is Matlab on my computer. And of course, I only like to use command prompt. So my Matlab is command prompt only. Those of you who don't have Matlab on your computer, no problem, that's okay. All you have to do is go into your VNC window and type this. Okay, so I'm just going to type that. I'm going to go back here. First, I'm going to change to my Scratch directory as always. Okay, now ml matlab /2019a, I think it was, right? Okay, all right. Press return. And you just wait a second, and we'll just eventually give you a success. All right. Ooh, what happened here? R, I forgot the R. Okay, here's a little trick. If I press the up arrow, it brings back the last command that I had, and I can just edit that command rather than retyping everything. All right, sorry, I forgot the R. Now, okay, good. Now I just typed Matlab, Matlab, and then I'm going to put an and the reason that I'm going to put an and is because I want, when the Matlab window opens, I want it not to occupy my command prompt. I want it to run in the background with it while leaving me access to my command prompt. So that and all it does is it makes my command prompt still active and available for me to use. So I'm just going to, type Matlab and press return, and it's going to start up Matlab. Okay. Okay, and here my my zoomed in version is working against me a little bit, so I'm gonna zoom out a little bit. Okay, so those of you who don't have Matlab on your computers will be able to access Matlab in your VNC window. Okay, and this is the default of how it opens. Okay. I hope that most of you have had some exposure to Matlab. Let me just do another very quick poll. Type in the window here if you have had no prior experience using Matlab. No experience using Matlab. Okay, a couple of people have no experience. That's okay. Matlab is a very easy thing to pick up. If you don't have experience using Matlab, it's okay. I'm gonna use very basic things here, and I'm gonna explain all of it as I go along. So it shouldn't be an issue. It should be really easy. For those of you who who want to learn more about Matlab, I believe that HPRC has Matlab tutorials available online. So if you have not had any exposure to Matlab before, but would like to learn more about Matlab, you can certainly watch those tutorials. And I maybe Lisa, if you are able to show us a link to one of those tutorials, then we could perhaps refer students to that. Okay, so if I go back to my command prompt here, you can see that I'm still able to use my command prompt, so that's good. I'm gonna go to my intro thing here, intro lamps, one visualizations. I'm gonna remove the DNA files, the DNA images, because I don't really need them anymore, and I like to keep things clean. So I just deleted those. And I'm just going to delete the structure file as well, so I'm going to get rid of that. All right. If I change directory to structures, right, go to structures, I should see 3 files that look like this. Okay. And I don't know if I have to re-add atomize, so I'm just going to try this without re-adding it and see what happens. No, okay. So I have to re-add atomize. That's ml atom I A3, okay, so you've all seen this before, okay. All 3 of these files that you see here are Atomi files that you can visualize, and the one that I wanted to focus in on here is this one, okay. I'm just going to show you again what it looks like before going inside. This one has a slightly different format than the one I was showing you previously. Okay, the format of this one is like this. It starts out by saying how many particles are there. Okay, so this one contains 1,000 atoms. What is the length scale that I'm using? So I'm using the length scale of angstroms. So 1 unit here equals 1 angstrom. This series of lines that come afterwards with the H's are telling me the shape of my simulation cell. So the shape of the simulation cell can be a cube, or it could be something that's not cubic. For example, it could be a parallelepiped, something that's skewed. But for now, I'm going to use just a cubic simulation cell shape. If I press return, it's going to allow me to scroll further through. It's got a lot of other stuff there. We're not going to pay attention to all of it. And then eventually when I scroll far enough down, I'll see that I have rows where each row begins with a 209.0, then PO, and then numbers, right? And you can see that some of these numbers are changing as I keep going down. These are basically atom coordinates, okay? So this is another structure file. It contains coordinates that shows you the positions of atoms, all right? I can see what it looks like by running atomi. So let me just run atomi on this file. Okay, and here's what I got. And expand this a little bit. Okay, I'm not going to use perspective view. I'm going to use orthonormal view. And when I rotate it, you can see that this is a crystal. Okay, I'm pressing function down, and that allows me to change the size of the atoms. You don't have to do this if you don't want to, but if you do function down, you can make the atoms look a little smaller. And so then you can, very clearly see that this is a crystal. Here I'm looking along a 100 type Miller index direction. Here I am looking along a 110 type Miller index direction. And if I rotate it like this, I can look down a 111 type Miller index direction. So this is a crystal. Atomi lets you do things like add bonds. So if I press B, it'll put bonds in, and I can see this crystal with bonds in it. Right? So all kinds of nice, neat stuff like that. So anyway, this crystal is a simple cubic crystal structure. It's a cubic crystal, and it's a simple cubic crystal. You guys have probably already, heard before about some different cubic crystal structures. For example, you've heard about face-centered cubic crystals. You've heard about body-centered cubic crystals. This crystal that I'm showing you here is simple cubic, which means that there's one atom at the corner of the unit cell, and that's it, right? So it's the simplest kind of cubic crystal structure that you can imagine. Cubic crystals, simple cubic crystals are not very common. In fact, in the periodic table, there's only one element with a cubic crystal structure. Anybody know what that is? Anybody know what is the one element with a simple cube? Polonium, that's it. All right, very good. That's, in fact, why we had that PO, right? So you remember I had the PO here. That's the symbol for polonium. And 209 is the atomic mass of polonium. So this is, in fact, a polonium simple cubic crystal that we're looking at, all right? So what we're going to do here is we're going to make ourselves our own. We're going to basically use Matlab to make this structure, okay? And I'm just going to walk you through it very briefly so that you know how to make a structure in Matlab. Really, all you have to do to make a crystal structure in Matlab is to write down the atomic coordinates and write down the size of your simulation set. Okay, so I'm going to close that down, and I'm going to go to my Matlab. And actually, since most of you don't have Matlab on your own desktops, I'm going to use the Matlab that's here on HPRC. So I'm going to log out of this. Oops, log out or quit. All right. So I'm not going to use my desktop version of Matlab. I'm going to use the one that's here on this virtual session. And I'm just going to, first I'm going to check to see if I'm in the right directory. So pwd, by the way, all the command line commands that you have in Linux should work in Matlab as well. All right, I'm in my Scratch directory, that's good. Let me actually go up to my LAMMPS, so cd intro LAMMPS and then 1 visualizations. And notice that I'm using the autocomplete with tab here as well. Okay, over here it shows me what's inside. So I see everything that's inside my directory up here. All right, so I navigated over. Everybody with me so far? Good. All right, so here's what I'm going to do. I'm going to imagine that all of my atoms are sitting in a cube with unit dimensions, right? So I'm basically going to imagine that my cubic crystal structure consists of atoms that sit in a unit cube, right? So the simulation cell I'm imagining here has units of 1 by 1 by 1, okay? And I'm going to place the atoms at locations within the unit cube that are equally spaced, okay? And I'm going to record the positions of the atoms in that unit cube. And after I'm done with all that, I'm going to specify the size that that unit's cube should be expanded to, okay? Because, of course, eventually I want to have all these positions written down in angstroms. So, you know, and to do that, I'm going to have to figure out what's the lattice parameter of polonium, which we'll do in a minute. But before doing that, I'm just going to put all the atoms into a unit cube, and then I'm going to say what that unit cube should be magnified to be. What should be the actual dimensions of that unit cube? Okay. So if I wanted to write one of these structure files, right, as I already told you, you know, I showed you what one of these structure files looks like. Oops. I don't know why it's not showing me. Okay, I know what is the name of the file, so I'm guessing it here. But maybe Lisa, maybe you know why it's not showing what I'm typing. But anyway, this file consists of a bunch of rows, which contains basically all the atom names, right? So what I'm going to do here is I'm going to just figure out a way to write down all these atom coordinates. Okay, and I'm going to do that in Matlab. Now, of course, you notice, by the way, that these coordinates that I have written here are also in a unit cube, right? So you can see, all the coordinates are fractional. They're not showing you 1 angstrom or 2 angstroms or 3 angstroms. They're showing you 0.1, 0.2, 0.3. You should never see atoms that are spaced less than about an angstrom apart. You know, you presumably know how large an atomic bond is. It's about an angstrom or 2. Right, so this automatically, just by looking at this, you can see this is done in coordinates that are not the real physical coordinates. These are actually just some reduced coordinates. Right. So all you really need to do is write out all these coordinates, and I beg you, there's a what I'm going to do here is I'm going to do a 10 by 10 by 10 lattice parameter model. So I'm 10 lattice parameters by 10 lattice parameters by 10 lattice parameters. That means that I'm going to have 1,000 lattice parameters altogether. 1,000 unit cubes, right? 10 by 10 by 10. 1,000 atoms, right? You remember when I did this more command, the first line here showed me that I have 1,000 atoms. Later on, that means I have 1,000 rows, 1 row for each atoms. Please don't ever do this by hand, right? You should use, if you don't like using Matlab, use some other program, use some other means. Don't do this by hand. Have a computer do it for you, okay? So that's what I'm going to do. I'm just going to go to Matlab, and I'm going to have Matlab do it for me. Now, the way that Matlab does things is you can write in scripts. You can write yourself little scripts that you can run. I'm going to do that. I'm just going to press new script up here. Okay, new script. That opens up a window here for me. And I'm just gonna press some carriage returns and save. So this script is gonna have a name. I'm gonna call it polonium PO crystal. Okay, and notice that it shows up in my visualizations directly, so I'm gonna save it there. All right. If I go back to the command prompt here, I can do ls, and now I see PO crystal. That's the script that I just wrote. And it also shows up here, right? Whenever I write something in this script, that basically is a command that I can execute in MATLAB by calling the script. So let's say that, I have here a equals 1, okay? That basically is a command that assigns the value 1, that creates a variable a and assigns the value 1 to it. So I'm just going to save. And now if I call this script PO crystal, oh. Am I in the wrong directory? No, here I am. PO crystal. Huh. Not sure why this doesn't work. Good work. Okay. Okay. Good. I know what went wrong. Let me start over so that everybody. This is really annoying. I don't know why it doesn't let me see what I'm typing. Okay. So I'm gonna do this again. A equals 1. Save. And I'm gonna write PO crystal.m. Last time I accidentally deleted this .m at the end, and that made it so that Matlab couldn't recognize it. So I'm just going to save it with the .m. All right. Now when I do ls, I see PO crystal with .n, and I should be able to run PO crystal. Okay, great. So this basically shows you that whatever I write here gets executed down here when I run PO crystal. All right. What am I going to do? All I want to do is I want to write myself a little loop that creates the positions of all the atoms in this crystal. So here's how I'm going to do that. I'm going to tell myself, first I'm going to specify how many unit cells I want there to be on each side. So I'm going to call that variable n. I'm going to say I want 10 unit cells on each side. So n equals 10. And I'm going to put a semicolon after it so that when I run it, it doesn't write n equals 10 to my screen. All right, so this is basically just going to suppress the output from that. And now I'm going to write a very quick script. Again, I'm writing this in Matlab, but if you prefer to use Python or something else, that's totally fine. So I'm going to use for loops for, actually before that, I'm gonna actually create the variables that I'm going to use to store the positions of the atoms. So I'm going to say x equals zeros n to the third 1. Okay, that basically makes a vector with n to the third zeros in it. Okay, and then I'm going to say I'm going to have a y coordinate, which is I'm going to initialize to be the same as the z, which is also basically just a bunch of zeros. All right, I don't have to do this. Matlab will automatically define variables as I create numbers, as I assign numbers to them. This is just sort of good programming practice. So this is the programmer in me saying I should define my variables. So anyway, so I'm going to do that. I'm going to use for loops, and I'm going to define a counter here for I equals 1 to 10. And then if I go through this for loop, I can put in I can put in values for some of my positions, right? So I could basically scroll across the 10 simulation cells that I have in my crystal, and let's see if somebody's asking something. Zoom in. That is not a colon; it is a semicolon. So I'll zoom in. Let me actually close this down. I don't really need this stuff. Let me get rid of this. Close. Close. All right. And that's the rest of my family coming in. So let me zoom in. Okay. All right, I'm zoomed in, but I think I'm going to have to go to a different different room if you don't mind. So give me just one moment. One moment, please. Sorry. No problem. It's okay. These are the joys of working from home. I get a sandwich brought to me, which is very nice, but then I have to move around. So sorry about that. We will figure this out. Okay, no worries. All right, so here we are in Matlab. I've defined my variables. There was a question here. So this is a semicolon that basically suppresses the output. Let me see if I can show the rest of this Matlab window. There it goes. All right, good. There we are. And now all I'm going to do is I'm going to run through and basically create a crystal structure by defining the x, y, and z coordinates in the unit cube, right? So there's going to be 10 unit cells along the x direction, 10 unit cells along the y direction, 10 unit cells along the z direction. So in this first loop, I'm just going to choose one of the coordinates to define, okay? And let me do one more thing here, actually. I'm going to define for myself a counter. This is just going to be a counter variable. Every time I go through one of these loops, I'm going to, up the variable. So this first loop is going to define for me, let's say, the x coordinate. Then I'm going to have another loop inside, which defines for me the y coordinate. And then I'm going to have another loop that defines for me the z coordinate. And they're all going to go from 1 to n. Okay? When I'm inside here, I'm going to up the counter by 1. Right? So basically every time I'm inside the inner loop, I up the counter by 1. And then I take the CT number entry in the coordinate for x, and I'm going to define that as I divided by n, right? So basically just fractional, right? So I is going to be initially 1, and then it's going to go all the way up to 10, all right? I'm going to define for myself y CT equals j divided by n, and z CT equals k divided by n. And then I'm just going to close everything down. Okay, everybody with me on this? Let's see what we got in the chat box here. Let's see, what didn't work? Was everybody able to start up Matlab? Was everybody able to write a script like this? Anybody able to write scripts like this? What is it that didn't work, Nadia? Was it the portal that didn't work? How did I get the n to show in blue? It just shows up in blue by itself, right? So Matlab automatically writes all commands in blue. Does it not show up blue on your screen when you do it? Well, you have these fors, right? For I equals 1 colon n. So, okay, I mean, if it doesn't show up in blue, that's weird. I've always had it show up in blue, but if it doesn't, it's fine. I mean, so long as it works, that should be fine. Okay, so I'm just going to go here, and I'm going to run my polonium crystal thing. And when I run it, I don't get anything outputted to the screen because I've suppressed all the outputs with the semicolons. But if I say who, that's going to show me what variables I have. And basically all the variables that I defined in this script are available to me now. And if I say size x, it'll show me that it's a vector that contains 1,000 entries, right? So I can do, for example, in Matlab, I can see, what I've created here, the x, y, and z coordinates. What are they? I can basically have a look at what they look like by using the plot3 command. This is not super important, so you don't have to, necessarily do this as I do it. But plot3 basically allows you to plot points in 3 dimensions. I'm going to plot them with a dot, and I should see my cubic crystal pop up here as a plot in just a second. There it is. Interact with trace. Okay. And let me actually just make axis equal. So this basically makes things. What did I do before typing the plot? Before typing plot, I ran my PO crystal script, right? So basically I wrote this script, I saved it, and I ran it. And what that did is it created for me the x, y, and z coordinates, which I then put into the plot command. Okay, you don't have to do this plot command. I'm only doing it so that so that you can see that what we came up with in the end is what we were supposed to come up with, which is basically just a, you know, a 3D crystal. So let's do this rotate 3D thing. Right, so Matlab allows you to rotate this and basically allows you to apply. You can see this is the 11100 direction again. You know, just as I was showing you in Atomi a second ago, this is the 110 direction. And this is should be the 111 direction right there. So you work enough with these crystals, you start to recognize the directions. Okay, so this is just to show you, you know, what I've done here, how to actually build this model. Okay, here's what I'm going to do next. I am going to take these coordinates that I wrote out, the x, y, and z coordinates, and I'm going to write them out to a file. And I'd like to write them out in such a way that I can, I'm not really sure why I still can't see. I'm going to write them out in a format so that they look like this, right? So in this format, I have 209 for the atomic mass of polonium. I've got the PO thing here. I've got the first 3 zeros that you see here are the positions, right? So in this particular file, the first atom occurs at the origin. I could have done it this way too, but in my script, I put the first atom at 0.1, 0.1.1 rather than the origin. That's okay. It doesn't actually matter because it's all under periodic boundaries, right? So I can shift this around. And these last 3 zeros are the velocities, and I'm just going to keep them as zeros, right? Because I don't want any of my atoms to have velocities yet. So I'm just going to keep all those at 0. All right. And so the last thing that I'm going to do here is I'm going to just put together something that I can, you know, easily write out this file. I'm just going to compile for myself a vector that I'm going to write out, and I'm going to use the DLM write command. The DLM write command is a command that you can use in MATLAB that very easily lets you write things to a file. By the way, if you are a user of MATLAB and there's a function that you know you haven't used in a while or you've never used it, you can always write help DLM write, you know, whatever is the command that you're interested in the command prompt, and it'll give you a help file, right? So it'll basically give you some help here on what's the syntax for using that command. Right, so this particular command, you just specify the name of the file that you want to, you know, have it write out, and then you put in the thing that you want it to write. Right, so I'm gonna give it an array of numbers to write out, which is going to contain all of my positions, all of my masses for polonium. It's also going to have, you know, the zeros padded with zeros over here for the velocities. DLM write. Unless I'm mistaken, I don't think DLM write actually allows you to write characters. It only lets you write numbers. So instead of polonium, I'm going to write pi. And the reason why I'm going to write pi, you know, 3.14159, is because I can then very easily just replace all pi's with polonium. Right. So I'm going to edit this afterwards, as you'll see in just a second. So DLM write. I'm going to choose for myself here a name of a file that has to come in single quotes because it's a character. So let's call it atom coordinates.txt. I'm going to make it a text file, and I'm going to write out a array m, which I haven't defined yet. I'm going to define it here. And the way you're define arrays in MATLAB is you just have these, you can put vectors into an array. I'm going to have x, y, z. I am going to have, let me just define for myself a little helper array. So helper array, I'm gonna actually make it a vector of ones and cubed. So this is a vector that contains only the number 1, just basically a bunch of number 1s. Okay, and I'm just going to do HA times 0. HA, so I'm turning those ones into zeros, HA times 0. And now over here, I'm going to do HA times 209. That's the atomic mass of polonium. And then HA times pi. And pi happens to be written in to Matlab. So now when I do DLM write, it should write out for me a file called atomcoordinates.txt, which has basically all of these rows in it, right? Except for instead of polonium, I'm going to have pi. All right. So let me go back here, and I will write for myself PO crystal. All right. Bang. There it goes. Let me go back here. I'm in the structures directory, so I'm going to drop down by 1. Let's see. I think that, you know, Lisa, were you saying just a moment ago how I can make the letters appear again?
Yes, so I'm not sure if this is a Safari and Chrome issue. Can somebody type in if they're having this issue in Firefox?
Let me just open a new terminal window.
Yes, opening a new terminal seems to work for most people.
Oh,
Unfortunately.
no. Okay.
Did you close the other one?
I closed the other one. Oh, no.
Yes, you cannot close the other one,
close
though.
the other one.
It will
Okay,
close your
geez.
session.
Right, fine. All right, so I have to restart this session. Sorry, guys.
So
Sorry
for those
about
of
that.
you who are having trouble with the text suddenly disappearing and not showing up when you type, please open a new terminal, and it should work in the new terminal.
But do not
Annoying,
close
I'm sorry, but it's a workaround. And but make sure you do not close the first terminal, otherwise it will close your session.
Okay.
Also, if you open a new terminal, you'll need to change to the correct directory. And please, if anybody's having this problem in Firefox, let me know.
Haha, I'm not the only one. All right, so by the way, if you go to utilities in Mac, and I don't know what the corresponding thing is in Windows, but in Mac, if you go to your to your applications folder and utilities, you see there's terminal. Right, so if you open your terminal window, I should be able to SSH directly to ADA, right? hprc.tmu.edu, like that.
Yes, but if you want graphics, you
I
would
have to
need
use,
the
I
dash
need
capital
to use
Y.
that. Okay. I don't think I have Xterm here, but is this the
Oh,
right?
yeah.
Is this the
That
right?
is
Or do I have to?
no HPRC.
No HPRC. Okay, so there we go. Yes. I just log in. And now I have to do duo. Okay, never mind. I'm not going to do this. I didn't even bring my phone here with me. So anyway, you do your dual push and then you log in. So basically, this whole thing that you see here, right? This guy that you get, on this virtual screen, you can just have it directly on your computer screen. This is, I think that for day-to-day work, doing it directly on your computer screen is much easier. And all you have to do is install X Windows so that you can actually have windows popping up when you type things on your command prompt. It's much, much easier and faster, and things, and you're not prone to, what your, issues that there might be with the browser that you have or whatever. So I'm going to shut this down. All right, let's see. If we wrote the Matlab script on the desktop app, do we have to upload it to the structures folder? If you wrote it on your desktop app, you can just run it on your desktop app. You can upload it to your structures folder if you want. You can just run it on your desktop, and then you'll basically get your file written out to your desktop, and then you can just upload the final file that we're going to be using for Atomai, and just use your HPRC window to just visualize that, right? So you don't necessarily have to, put all the intermediate steps onto your HPRC thing. So now I have to actually, let's see, I have to actually go to Scratch again. I am, intro 1. All right, and I need to ML Matlab R 2019A. Okay, so it's going to add Matlab. But in the meantime, let me just point out, you remember, oh, what did I do wrong this one? Oh, it's not 2109. It's 2119. Okay, it's 2019. All right. So anyway, you see that last time when I ran my PO crystal script, it actually generated this atom coordinates.txt file. So I'm just going to look at what that looks like. Atom coordinates. Oh no, it's delimited by commas. That's no good. I'm going to have to open Matlab again. And I'm going to change the delimiter so it's not delimited by commas. So give it just a second and I'll be right there. There we are. Okay, cool. It even opened up the script. So basically I'm going to go down here, comma, single parentheses, space, single parentheses, close. That changes the delimiter to a space. Where am I? Visualizations. Good. Okay, PO, crystal. All right. And now when I go back here, oh, I didn't press and. Drat. All right, so let's open a new external. All right, now let's look at atom coordinates. Yay, okay, now it's delimited by spaces, not commas. Good. We're almost done. So I'm going to go back to my interactive session. I'm going to open my Scratch directory here. And here I am, I'm gonna just navigate into this visualizations thing. And I'm going to go to structures. I am going to I'm gonna select this thing and I'm gonna press edit. Okay, and you see how that opens up an editor in my screen. So you can edit all your files, all the files from HPRC, you can just edit them directly in your browser using this editor feature. What I'm gonna do is I'm just gonna select everything here all the way down to this point. I'm just gonna select all of it all the way down to here. And I'm gonna copy. Copy, all right? And I'm gonna close the editor. All right, and now I'm going to go back here and I'm going to open my atom structures. I'm going to select my atom structures, edit that. Okay, I'm going to go all the way up here, put a few spaces, put this thing in here and paste. So basically I just pasted the header from the other file. You see, no need for you, I mean, you can write yourself a Matlab script that writes all this header. It's not too hard, but you don't have to. You can just cut and paste the header. The only thing that you need to know from this header is that this number 33.6 is 10 times the lattice parameter of polonium in angstroms. Okay, why 10 times? Because we're doing 10 unit cubes on the side, right? So each of these this structure contains 10 unit cubes of polonium on each side. Okay, so the lattice parameter is 3.36 angstroms. So if I have 10 of those unit cubes, then my entire model is 10 times that, so 33.6 angstroms. And so this H11 is telling me the dimension in the X direction. This H22 is telling me the dimension in the Y direction. H33 is the direction in the Z is the dimension in the Z direction. Okay, so this particular model has the same dimension in all directions. So I just put 33.6 in there for all the things. I have 10 times 10 times 10 atoms, 1,000 atoms. So I'm just going to keep this at 1,000. Okay, so I'm not going to change that. I'm going to just keep that at 1,000. And I'm almost done. The only thing that I have to do now is I have to take this 3.1416, which is rounded off version of pi, and change it to polonium, right? So I'm hoping that I should be able to go up here and search. Let's see, where's search? Do I have search? Find, search, no. Maybe it's not gonna let me search. Not gonna let me search. That's okay. I'm just gonna save this. Okay, so it's saved. I think I can visualize it even if I keep it as pi. It's just that all the atoms are gonna show up as pi when I do atomize. So I'm just gonna go back here to atomize. Okay, I'm going to actually change the name of this from atom coordinates to something else. So rather than calling it atom coordinates, I'm going to call it my PO dot CFG. CFG is the name of the file format that uses that particular header. Okay, so I'm going to do that, and all that that does is it renames it. You know, so it renames the file so that whereas before it was called this, now it's called this. I think I have to add in atomi again. So atom I A3. There it goes. All right. And now just A3, my polonium, bang, there it is. See, your very first crystal structure. And you made it yourself. Congratulations. Okay. So this is how you make models. And if you want to, you know, if you wanted to make a more complex crystal structure, you would basically have to change, you know, the locations where you're putting the atoms. But this is basically how you would do it. All right. So very, very simple intro to how to make crystal structures. And you can use LAMMPS, you can use anything you want. If any of you want, I can share this script with you. You know, if you want me to give it to you, I'm happy to give you the script. But as you can see, it's really just, you know, it's super simple. All I'm doing is I'm looping over the unit cells and putting atoms into their appropriate positions based on where the unit cells are in the model. And at the end, I'm just writing it out. Right? So that's really all it is. And for this particular file format, the .cfg file format, all I have to do is remember to put on that, this header, right, which I just cut and paste. Okay, so making these crystal structures is pretty easy. All right, let me exit from this guy. I'm going to quit Matlab now. All right. Let me go over to structures again here. This my subscript po.cfg is really identical to this thing, right? Simple cubic polonium.cfg. Very, very, very simple. Now the next step for us might be to say, well, what if I wanted to study not a perfect crystal structure, but a crystal structure, for example, that has a defect? And what's the simplest kind of defect that we can possibly imagine? Well, a vacancy is the simplest kind of defect. So let's say I want to make a vacancy. I am going to use the polonium structure that I have here to show you how to make that. Okay, so I'm going to take this my polonium, I'm going to copy it. So the way that I do that in the command line is I just do cp my polonium and I copy it into something else. So I'm going to call it my polonium-vac for vacancy. Okay, when I do that, I'm going to see a new file here called this. And of course, this file is identical to this one. It's a complete duplicate, same thing. Okay, but I'd like to make a vacancy. So the way that I'm going to do that is I'm going to go back here. I'm going to reload because I changed some stuff. So I'm going to reload. Okay, now you see this vacancy file. So I'm going to select it and I'm going to edit. Here we are. How do I take this single crystal and make a vacancy? Well, all I do is I take an atom and I delete it. That's how you make a vacancy. Does it matter which atom I delete in this model? Anybody? What do you think? Does it matter which atom I delete? Let's see. It matters. Any other votes? So I submit to you that it does not matter which atom you delete. And the reason why it doesn't matter is twofold. First of all, this is a crystal, right? Every atom has the exact same neighbors, right? The arrangement of atoms next to every other atom is the same, right? So, so from that perspective, all the atoms are equivalent. It doesn't matter which one you delete. Moreover, you might say to yourself, well, okay, but it's going to matter if you delete an atom at the corner versus an atom in the center. And of course, that would matter if I was dealing with a nanoparticle, for instance, that had surfaces. But I'm dealing with a material here that's under periodic boundary conditions. You remember that periodic boundary idea that I introduced to you when the session got started? I can translate this model. So any atom that's sitting close to one of the boundaries can actually be moved over so that it's sitting in the center, and then other atoms are close to the boundary. So the positions of all the atoms are actually indeterminate to within a rigid body translation within the simulation itself because of the periodic boundaries. And so all the atoms in this model are really strictly equivalent. It's not going to make any difference which of these atoms I delete. I'm going to get an absolutely identical, completely equivalent defect structure in the model, right? Now, of course, if I had a more complex model, for example, a model with free surfaces or a model with other defects or a polycrystalline model or something like that, then of course it would matter, right? It would make a difference where I make the vacancy. But in this particular case, it's not going to make any difference where I make the vacancy. So I'm just going to take this first row and I'm going to delete it. I'm just going to make the vacancy here. Okay, so I'm just going to delete this row. Okay, it's deleted. Now, how many atoms do I have in my model? I used to have 1,000. I deleted one, so I have 999. I'm going to save that. Okay, save. All right. So now let me go back here, and I'm going to just do atomi again. A3 my polonium -vacancy.cfg. Oh, all right. I guess you have to do this separately in each terminal window, maybe? All right. There we go. So here I am in my polonium crystal. Again, I'm going to increase the size of the atoms a little bit. And let me just scroll this up, and I'm going to rotate. I'm going to see if I can find that missing atom. I don't see it. Let me see if I start moving this around if I can see it. Ah, there it is. You see that? It was a little bit hard to catch, but there it is. There's the missing atom. Interestingly, atom I, when it started, must have shifted the structure under periodic boundaries to begin with. So I'm just going to shift this around a little bit under periodic boundaries. You see that missing atom is right there. If I put in the bonds, it doesn't really do the bonds, does it? Okay. Hopefully you can all see that missing atom is right there. It's not always easy to see a vacancy. So atom I actually allows you to do some nice things to make it easier to see vacancies and other defects. For example, it can color atoms according to the coordination number. So let me actually show you how to do that. First thing I have to do is adjust the interatomic distance. So I'm going to press R. Okay, and this tells me what is the distance between atoms that I should use. So I'm going to use 3.36 because that's the lattice parameter of polonium. Okay, just going to use that. I hope it got it. Maybe it didn't. 36. No, it's not doing it for some reason. Let's try it like this. No. Let's do 4. Nope. Not really sure why it's not cooperating. Well, I might not be able to show you how to do the nearest neighbor coloring if I can't change the nearest neighbor distance. Okay, let's do this. R, I'm gonna press R, and then here I say control home. It's not letting me do it. Okay, I might not be able to actually show you how to do this in this particular window, but hopefully just by making these things a little bit bigger, and moving this around, you can see that there is an atom missing, right? So this is how you would see a vacancy. This is how you would make a vacancy. Okay, I'm gonna stop the vacancy presentation, part of the presentation there. And just come back here for a second. This vacancy structure that I just made, very simple. But if you just look at what's in the structures file here, you see that this structure file also has this sc-po, sc subscript po-vac. It also has this vacancy file there. I have another file here called sc subscript po-fs. That's a free surface file. So basically, all I've done there is I've changed the dimensions of the model so that I get a free surface showing up. So let me show you how to make a free surface. I'm just going to go back down here, and I can't see the text again. So let me make a new X term. I'm not going to shut down the old one this time. Okay, I'm going to copy my po.cfg, my po dash surf. Okay, this is going to be my surface file. All right, I'm going to go to my editor. So I'm going to close this, reload, and here's my surface file. I'm going to open that, edit it. And your first thought might be to say, well, if I want to make a free surface, all I have to do is just increase the dimensions of the simulation cell in one direction, right? Because I've got only 10 by 10 by 10 unit cells. So if I just double, let's say, the dimensions in the z direction, then that should create for me a free surface. Now, it turns out that it won't, and the reason why is because all of these atomic coordinates that I have down here, as you recall, are written down in a unit cube, right? And basically, whatever I write in here is going to stretch out all the coordinates in the unit cube to whatever shape that I give to the unit cell. So let's say that I double this, right, from 33.6 to 67.2, right? So that's double, right? And let's say that I do save. I'll just go back here, and I'll try to visualize this. I think I'm going to have to do ML atom I again, aren't I? So let's just do a quick check here. Yep, ML atom I A3. Looks like I have to do this every time for a new terminal window. So All right, so let's do A3 mypo-surf.cfg. Right, so here's that file that I just made where I've increased one of the dimensions. Now, of course, now you can't see it because that dimension that I've increased is going into the model, right? But if I rotate, you'll see that one of the dimensions has gotten twice as long. And the spacings of the, and what that basically did is it just increased the spacing between the atoms in that direction to be twice as much as in the other case, right? So this isn't really what I was after, right? I wasn't trying to do this. I was trying to do something a little bit different. So if I want to make a free surface, so increase the size of the model so that I have some empty space and a free surface, what I actually need to do is I have to go back to my Matlab script that I had before. So let me exit. I'm going to do Matlab again. Unfortunately, I can't see what I'm typing, but all I did is I typed Matlab. That's if you wanted to make a, you can type xterm and if you wanted to make a new xterm from an existing xterm. Okay, so Matlab is coming up. All right, and I'm going to open up my script. So open PO crystal, right, the script that I had before. I'm just going to edit it. So here I had z divided by n, right? But now I know that I'm going to make the model be twice as large in the z direction so that I can put in a free surface. So I'm going to divide this by 2 times n. Basically, I'm going to make the spacing of the atoms smaller. I'm still going to output them scaled to the unit cube. Okay, so I'm still going to do all the output the same way as I did before. So save. I'm going to run PO crystal. There it goes. And I believe that's all I need from Matlab, so I'm just going to quit. Okay, and here's my atom coordinates again. There it is. I'm going to open up a new window so that you can actually see what I'm doing. So scratch. All right. And now I'm just going to rename atom coordinates to mypo-surf.cfg. Right, so I'm going to take those coordinates that I just wrote out from Matlab, and I'm going to move that to this surface file. By the way, if I look at what that looks like, it doesn't have the header yet, right? It's just got, you know, the atom positions. So now I have to go to my editor, and I'm just going to look again here. So open this guy, edit. I'm going to once again take this header, copy it, close. I'm going to take this, edit, paste the header. There's my header. 1,000 atoms just as before, except now I'm going to increase the size. 7.2, save. And now I should be good to go. So let's go back here. Here I am. Of course, this is a new window, so I have to once again add atomi. By the way, if you guys had a X terminal that didn't like periodically stop showing you the text, you wouldn't have to keep doing this. So this is sort of my kludge. Maybe if we figure out for next time whether this is a Safari issue or some kind of other issue, then I'll just use some other browser. Okay, my po-surf. I should be able to now see a nice surface file with a free surface. Yay, okay, there it is, you see? I'm just going to increase the size of these atoms a little bit. By the way, when I look at that, at this model, it seems like I've got a gap here. Is there actually a gap there? No, because if I shift this model around under periodic boundaries, you see the atoms are just shifting. Right? There's basically the same spacing between all the atoms. It's just that it seems like there's a gap because that's where the periodic boundaries are. Now here, of course, there actually is a gap because I've introduced free surfaces up here and down here. Right? So the way that I'm modeling the free surface, notice that, by the way, I still have periodic boundaries in the z direction. Right? So if I were to translate this in the z direction, I still have periodic boundaries. It's just now I have this big gap, right? And this gap, of course, is much, much larger than the interaction distance between atoms. And so these atoms here are going to feel like a free surface, and these atoms here are going to feel like a free surface. So this is how I've made a free surface. All right. So I think this is really basically all that I wanted to show you in terms of the demonstrations for today. Now, if you look at your directory here, so let me, sort of inconvenient to do it in this X terminal just because it keeps blanking. So let me just go back to this file transfer area. I'm in the 1-visualizations folder right now. I talked about this visualizations PDF file, right? So that's basically contains everything that I said today. This is what I wrote in Matlab, my little script that I wrote in Matlab. These are the 3 different structures that I made in Matlab using my little script. Those same 3 structures are the ones that I'm giving you here, right? So if you wanted to verify that your structures are working properly, you can compare them to the ones that I have here. They should be equivalent, right? I also have another folder here called exercises, okay? This is homework, right? So let me just download this, right? This is what you got, right? You've got a little bit of homework here. I'm telling you, now you should be able to create another crystal structure. So I'm telling you to create a crystal structure of an FCC metal, so gold in this particular case. I've given you the lattice parameter. I'm suggesting that you do a 5 by 5 by 5 cubic unit cell, and just do this gold crystal structure. You should be able to visualize it. You should be able to make a vacancy. If you go back to the notes that I gave you, it tells you how to actually look at just the nearest neighborhood of the vacancy. So you can look in the notes and it should show you. And then the last thing that I ask you to do is just to make a free surface of that gold structure. And then I just repeat the same thing with a BCC crystal structure, right? So this is alpha iron, the low temperature phase of iron. And what I'm suggesting is just do the same thing with alpha iron. This will give you a little bit of practice on how to make crystal structures, how to make vacancies, how to make free surfaces, and how to visualize all these things with Atomeye, okay? So this is homework for next time. I'm not gonna check your homework, right? I mean, this is basically just for you to be able to get a little bit of practice with this and be familiar with these tools. In the next session, what I'm going to do is I'm going to start talking about calculating the energies of crystals, calculating the energies of crystal structures with and without defects in them, relaxing those crystal structures. And so, my hope is that you'll get proficient at being able to construct some of these basic structures so that you can then proceed to start relaxing them. Let me just move over to this section here, which deals with the next tutorial. So I'm just going to download this tutorial here. If you want, you can pre-read some of these notes that I have on here. So the notes begin with a very basic introduction to what classical potentials are and how you can use those potentials to model forces between atoms. I am not going to spend much time at all trying to teach you this, right? The theory behind, how these potentials are built and how you use them in LAMMPS. I'm not going to do that. So if you want to, just pre-read this 1 or 2 pages before Thursday, that would help us a lot. And then basically next time what I'm going to do is I'm going to start up with this part here, which is basically just taking a crystal structure and running LAMMPS on it, okay? As I said, we're just going to calculate energies and then relax the crystal structures once we get LAMMPS up and running. So it's going to be, I'm just going to be basically trying to make you users of LAMMPS. I'm not going to try to make you developers of LAMMPS. So if you want a little bit of background, then please do a little bit of pre-reading just to make sure you're up to speed. During this tutorial on Thursday, I am also going to be talking about vacancies, right? So if you go down here, eventually I'm talking about relaxing crystal structures. I'm going to be talking about vacancies, but I'll also say a few words about self-interstitial atoms, right? So you know that vacancies are point defects in a crystal. Self-interstitials or interstitials are also defects in a crystal. Self-interstitials are a type of interstitial where you have an extra atom which is of the same type as the crystal. If you have an interstitial that's of a different type in the crystal, then that would be called a interstitial impurity, right? So for example, if I have a carbon interstitial in iron, the carbon is an interstitial impurity. But if I have an extra iron atom in iron, then that's called a self-interstitial atom. So in this next tutorial, I'm going to talk a little bit about vacancies. I'm also going to talk a little bit about self-interstitial atoms. And the reason why I'm going to talk about self-interstitial atoms is because they're just a little more interesting than vacancies. Vacancies are the simplest and arguably the most important point defect in the crystal, but self-interstitials are just a lot more interesting to look at. If you have not worked before, if you haven't had any background, prior background on point defects in crystals, in particular, if you've not had any background on interstitials in crystals, I have here in under the second part of this tutorial, 2-energies, I have something here called point defect crash course. So if you open it up, there's a single PDF file in there. Just going to download it so that you can look at it. It just has a few slides here that talk about point defects. If you have a few minutes, please take a moment to look through these slides just so you can become familiar with the idea of a point defect, so that once we actually go through the tutorial on Thursday, you will be able to follow along and understand what exactly we're doing. Actually, since we have a few minutes left in today's session, what I wanted to do is just spend a few minutes to go over this information about point defects so that we're all ready to go on Thursday. So very, very quick introduction to vacancies in self-interstitial atoms. So I'm going to stop sharing my overall screen here, and I'm just going to share this PDF file so that you can see the whole thing without getting it cluttered with other things. So formation energies of vacancies. What is a vacancy? Vacancy is when you take an atom out of the crystal, but you don't just get rid of that atom. You have to put it somewhere, right? And we imagine putting that atom at some location where it will not change the surface energy, right? So what we like to do when we think about making a vacancy is we imagine taking the atom out and putting it on a kink on a surface, okay? The reason why we put it on a kink on a surface is because the total surface area remains constant as a result of that. It doesn't change, right? If I put an extra atom here, then these dashed lines become new surface area, but these solid lines are no longer surface area. And you can just very easily see that the amount of surface area has not changed if I put an atom onto a kink on a surface, right? So the surface energy hasn't changed. The number of atoms hasn't changed. The only thing that's changed is that now I have a hole inside. And so if I compare the energy of the crystal before and after this operation, that gives me the vacancy formation energy. Okay, so one of the things that we're going to do next time is we're going to actually calculate using LAMMPS the formation energy of a vacancy. Okay. If you were to look into the literature, you can see that there's actually a lot of information on vacancies already. So for example, the vacancy formation energies for a bunch of different elements are known. So here, basically just a bunch of different elements. They have different crystal structures, and here are the corresponding vacancy formation energies. So you can see for silver, vacancy formation energy is 1.11 electron volt. For aluminum, it's lower at 0.67 electron volts. Copper, is 1.28 electron volts. Okay, so these are the vacancy formation energies. For reference, I'm also listing the cohesive energy per atom. So basically, that's just how much energy each atom in the crystal has. That's also information that we're going to need. We're going to compare this against our LAMMPS calculation next time. And here's some other information: vacancy migration energies, vacancy formation relaxation volumes. I'm not going to talk about those things next time in the simulations that we do next time, but I just wanted to list them here for completeness sake. Okay. When you talk about a self-interstitial, you're basically just performing the very opposite operation than what you had in a vacancy. In the case of a vacancy, you were taking an atom out of the interior and putting it on a step on the surface. When you think about an interstitial, you take an atom off of a step on the surface and you put it into the interior of the atom. Into the interior of the crystal. That's how you make a self-interstitial atom. If you were to look at self-interstitial formation energies for different crystal structures, here's a bunch of those self-interstitial formation energies. You can see that they're actually much bigger than the formation energies of vacancies. So the formation energy of a self-interstitial in copper is 3.23 electron volts. Compare that to the formation energy of a vacancy in copper, 1.28 electron volts. So it's almost 3 times as high. Self-interstitial formation energies tend to be much higher than the formation energies of vacancies. Okay, and we're going to be able to see that when we calculate the energies of those defects using LAMMPS. So you'll be able to do that at the next tutorial. The other reason why I like to use self-interstitials as an introduction to LAMMPS is because when you think about it, if you're interested in creating a vacancy in a crystal, there's only one way to do that, right? In a single component crystal, there's only one way to make a vacancy, and that's just you remove an atom, right? So therefore, all possible vacancies in a single crystal have exactly the same structure, right? They look exactly the same. However, if you're talking about self-interstitials, there are many different ways to put self-interstitials into a crystal. And the structure of the self-interstitial will be different depending on where you put it, right? And so presumably, many of you have had an introduction to crystal structure, and you've probably seen some of these different varieties of point defects. So for example, these are the types of interstitials that you can have in a face-centered cubic crystal. If I were to put an interstitial, which is labeled here as the black atom, if I were to put it into this location in a face-centered cubic crystal structure, this is called an octahedral point, an octahedral interstice in a crystal structure. And an extra atom that I put into this octahedral point is called an octahedral interstitial. On the other hand, if I were to put an extra atom into this point, that's called the tetrahedral site. That would be called the tetrahedral interstitial. And those are sort of the two most commonly learned interstitial structure, but there are a number of other ones also. So if I put an atom in between 2 nearest neighbor atoms, that's called a crowd ion. And then you have these kinds of interstitial structures, which are called split dumbbell configurations. And split dumbbells are a kind of interstitial where which are created a little bit differently. So in all of these interstitial structures up here, you just take an extra atom and you put it in. For these split dumbbell structures, it's a little bit more complicated. You start out by taking an atom out, right? So you make a vacancy, and then you replace that atom with 2 atoms. Okay, so a split dumbbell is where you've replaced 1 atom with 2 atoms. And that's why it's called a dumbbell, because, you know, whereas you had one atom before, now you have kind of like a dumbbell of atoms. Depending on which way this dumbbell is pointing, you can get different structures. So a 100 split dumbbell is a interstitial where the dumbbell is pointing, is aligned with a 100 Miller index direction. A 110 split dumbbell is a split dumbbell which is aligned with the 110 Miller index direction, and then a 111 split dumbbell is aligned with the 111 Miller index direction. If you were to look at other crystal structures like BCC or HCP, you also get different kinds of crystal structures in those. You also get different kinds of interstitial structures in those other crystals, right? So interstitials have a variety of different structures. That makes it, I think, much more interesting to look at them, right? When you actually look at what they look like in Atomi, for instance, it's much more sort of gratifying to see them because they look kind of interesting. Just to give you a sense, right? So here I'm showing you some visualizations of copper with different defects. So this is copper with a vacancy, and I've labeled all the atoms that are immediately adjacent to the vacancy as big yellow atoms. And mainly because if I didn't do that, then you would have no idea where the vacancy is, right? Vacancy has such a small effect. It's such a small perturbation to the crystal structure that you really don't see anything. Here is a 100 split dumbbell interstitial. It's got a much bigger perturbation. So in particular, you see those two big gray atoms. Those are the atoms of the dumbbell, right? So you can clearly see them, right? They make for a very, easy to spot perturbation in the crystal structure. When you look at those yellow atoms that I've indicated, which are just the neighboring atoms of the dumbbell, you can see that some of them are massively displaced from their equilibrium perfect single crystal locations. Perhaps that's a little bit more easy to see from this 110 perspective, right? Where you can see that some of those yellow atoms are really kind of pushed out a lot by the split dumbbell. And so, the split dumbbell, this self-interstitial structure, strains the neighboring crystal much more severely than a vacancy does. And it makes it much sort of more interesting to look at. So we'll do this a little bit next time, and you'll see this a lot more easily next time. But for today, I just wanted to give you this very brief primer on point defects so that when we get started again on Thursday, we will be able to jump in and just start looking at these defect structures. Okay, so I'm going to stop here, and I'm going to see whether anybody has any questions before we end the session for today. So any questions on today's session? Okay, if any questions do come up, please don't hesitate to either email me or ping me on the Slack channel. I'm happy to get back to you with any questions that you might have. Again, if you have time, please go over some of the notes that I gave you. Please do try to do the exercises that I gave you from today's tutorial, just so you get some practice building crystal structures and making defects in it and so forth. And then next time we'll hopefully be able to just get started really fast and move on to doing LAMMPS. The tutorial stuff that I put up in there should also give you some information on how we're actually going to do how we're actually going to run the LAMMPS program. So if you feel like it, if you want to, feel free to work ahead. If you want to work ahead in this tutorial, that's absolutely fine with me. Yeah, and that's it. Quick question here from one of the participants. Don't see the homework in my directory. I was wondering if there was any issue on my end. So just by way of reminder, I'm going to sort of go back to my screen sharing here. I'm going to share my Safari screen. There we go. All right. So you remember, so I'm going to drop down to my Scratch directory. This is my Scratch directory. Intro subscript LAMMPS. This is the file that you guys got in your Scratch directory when we did that unzip command. I'm going to go into that file. The visualizations module is the one that we were working on today, so I'm just going to double click on that and go inside. Okay, and you see that there's another directory here called exercises. And in exercises, there is a PDF file called E1 subscript visualizations dash solutions. Okay, this is the homework file, right? So this is it. If you press download, you can see what's in it, right? So I'm not sharing that screen now. So let me actually share my whole screen so you can actually see what I've downloaded. Here's what I just downloaded, right? So this is the exercise file. It just gives you some problems, right? It doesn't give you any starting files to work with. Why? Because I'm assuming that with everything that you've learned today on how to build these files and using Matlab and modifying the files and running Atomai and all those things, you should be able to, you know, just read these problems and do these exercises yourself. Okay. Any questions? Any other questions? I don't see anybody giving me any questions. Let's see. All right. Well, if there are no questions, then just, you know, do this, and I'll see you on Thursday, and we'll pick it up from there, and we'll continue doing the LAMMPS tutorial there. For those of you who are interested in Ovito, please email either at Vika or Chris or Mac, and they'll do an Ovito tutorial for you so that you can use that visualization software if you prefer. Okay? Thank you very much. Bye-bye.